All right, so we're going to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1. So this graph here, the x and y axis, so the lines y equals 0 and x equals 0, and the line x equals 1 about the x-axis. So let's write the coordinates of these points here. That'll be at 1, 2. This will be at 0, 1. That, of course, is the origin, and that's the point 1, 0. Now, what we're going to basically do, if you want to revolve this, I won't shade it too dark because I want to draw in there. We want to rotate this shaded region about the x-axis, or I'm sorry, about the y-axis like that. So you're going to get some sort of like a cylinder with like a hole taken out. So let me try to draw this. Let me do it below so I don't waste too much space. But it's essentially a cylinder. So let's actually break this up into parts first. So then this can make a little more sense about what I'm talking about. So let's just first think about if we're just going to rotate like if our integral only went up, only covered this red square. If we're going to revolve that red square about the y-axis, then you're simply just going to have a cylinder, right? Because spinning this around the y-axis, we just get a cylinder. That sort of thing, right? So you get a cylinder, but this other part here did revolve this region. Let's trace it in green. You're gonna get like an outer cylinder part with like a bowl taken out of it. So from here upwards. Oh no, my green is dying. No. No. I think I have a backup. Backup green. All right. To the rescue. This we'll have this guy. We're gonna have this whole sort of thing in here. For that top portion. You can kind of get the picture. So the key to this problem, finding the volume of this, is to break it into two actual integrals. Because finding the volume of this red region rotated about the y-axis is simple because it's just a rectangle. It's just a rectangle being revolved around the y-axis. So the volume of this part would simply be pi times the integral from 0 to 1 from r of y distance from here to here. That's your r of y. This length here, and it's always the same. That's always going to be 1. So we have r of y squared dy. That's how the general equation. So for that part, it'll be pi times integral from 0 to 1. This outer radius, this is just again 1. It's always a length of 1 away from the axis of rotation. So it'll just be 1 squared or 1 dy. So we'll leave that here for now. But now we need to add this to the integral of this green region revolved around the y-axis. So here you actually have two parts. What we're going to do is we're going to have an outer radius, which will be the length from the y-axis to the edge of this. That'll be your large R of y. So this plus integral, and this pi will be multiplied by everything. So this, we're going from 1 to 2. The outer radius, R of y, in this part will just be 1. It's always 1 away. So again, we'll have just 1 squared minus small r of y. And the small r of y will be the distance from here to here, from the y-axis to this inner edge part here. And that's going to vary. You know, see, it's getting larger at this edge all the way over here. The length is 1, but over here it's 0. So again, it gets, you know, increasingly large as we go up. So small r of y squared. This whole thing will be multiplied by dy. So we got to figure out what r of y would, small r of y would be. Now, we just have to find an equation for this graph right here. Now the equation, if it was a function of x, would be y equals x squared plus 1. But we're now revolving, you know, around the x-axis. We're revolving, you know, around the y-axis. So it's going to be a function of y. So essentially, we just have to solve this equation for y. So let's actually move this over here. So we can then we'll have, let's take away 1, y minus 1 equals x squared. Take the square root of each side. We'll have the square root of y minus 1 is equal to x. And this will be our small r of y. So small r of y will be the square root of y minus 1. And this is r of y squared. So then this squared, it just undoes the square root. So r of y is simply just y minus 1. And so this part here just becomes y minus 1. So let's set up this integral down here. So plus the integral from 1 to 2, y 1 squared is 1, minus y minus 1 here. Y minus 1, because we already took care of the squared. So 1 minus y minus 1. So it becomes 1 minus y minus a negative 1, so it just becomes 2. So the second integral, let's not interfere, will be integral from 1 to 2, 1, so 1 minus negative 1 again is, this will be 2 plus y dy. All right, and then hold on a second, let me make sure I didn't mess up. So 1 minus a negative 1. So yeah, 2. Yeah, I got it. So 2. No, well, 2 minus y. Whoops, minus. That's what I knew. Something didn't seem right. No worries, I got the white out to the rescue. We got 2 minus y dy. So then we just integrate. So then we just solve this. Integrate that. So putting it all together, this looks like Christmas. So let's put this integral down here organized. The total volume will be pi times the integral of from 0 to 1 dy plus the integral from 1 to 2 of 2 minus y dy. So that's where we're going to integrate. And so let me just move us on to another sheet of paper because it's like I needed more space and when explaining this, no worries. So let's just work this out then. Not a problem. This is child's play at this point of calculus. So pi times integral of 1 dy. That'll just be y from 0 to 1 plus the integral from this one, 2y minus y squared over 2 from 1 to 2. Working it out, pi times all of that. This will just be 1 minus 0. So it'll just be 1 plus, so 2 times 2, so 4 minus 4 y squared over 2. So minus 4 over 2, so 4 minus 2, minus 2 times 1, which will be 2, minus 1/2 dy, and then pi times integral 4 minus 2, 2 minus 2 minus 1/2, so 2 minus 1/2, so 2 minus 3/2. So we'll get 2 minus 3/2, we'll get 1/2 in this whole thing. So we'll get 1 plus 1/2. So we'll basically get as our final answer 3/2 pi. All right, so that's our volume. All right, so there you go. I hope that helps. Good luck.